Yeah. Hello, students.
Yes,
Good.
sir.
Yeah. Good morning. Yeah.
Good
Okay.
morning, sir.
Mm, yeah. So, any questions? Let's wait for 2 minutes so that others will join in the meantime. Yeah. So, okay, let me share the presentations. Uh, okay. Okay. So, can you see the slide here? Multi-process. Hello.
Yes, sir.
Yeah, it is visible. No? Good, good. Okay. Yeah, let me put it in slideshow mode. Okay. Yeah, this is the one. Okay. Yeah. So yeah. Let's start the lecture. Today what we do is that today is it's a 2 hour lecture. So we'll take a break after about 45-50 minutes in between. And at the initial at just 5 minutes, we'll just try to conclude the introduction to this architecture, and then we move on to the next one, next topic, that is instruction set architecture. Basically, we'll see that what are the various types of instructions that can be used to represent the high level language to perform the different actions by the hardware and all. So before going to that, let's just complete the introduction. So in the last class, we discussed about basically the most of the time we'll spend for how to evaluate the performance. Basically, there are different ways to evaluate, but we'll try to focus on the evaluation with respect to the response time, that too also the single task. That means given a task to a computer, and then how the computing time will depends on the various factors like basically the first thing is that the complexity of the program and all that provides you that number of instructions, and then the capability of a compiler. That means we have seen that using a numerical example, if you use the two different types of compilers which derives the two sequences of instructions and all, so with that actually we can able to see that which is better. And likewise with respect to clock rates, so these are the things that we have discussed in the last class. And as we have seen that the performance depends on the clock rate or a clock period, the cycle period and all. So as you keep on growing the clock's rate, obviously the performance will be improved. But there is a limit for that, because as you keep on growing the clock rate, the power dissipation will increase. So to control that, initially the voltage that was given for the device, that has been reduced from 5 volts to till 1 volt. So with that, the power can be limited even though if we increase the clock rates, but again cannot decrease the voltage further, still further. So there is a problem with cannot increase the clock rate beyond certain limit and all. So that's known to be a power constraint. And so to handle that, but still if you want to further improve the performance, we cannot increase the clock rate. Okay, the other way is that by providing the multiple process instead of one processor. If you can able to design in a single chip, if you can able to employ a multiple process, where with that we can limit the like a power. That means by limiting the without increasing the clock rate further, and can also improve the performance. So that was the idea about this multi-process and all. And if you see the details like multi-core process, multi-process, where one more than one process will be there in a chip, and with that you can able to limit the clock frequency. But to provide the efficiency or enhancement in the performance using a multiple process and all, it requires a parallel programming, because since we have a multiple processors are there, so we have to effectively use the process whatever is present in a single chip effectively, so that the performance can be improved. So for that, what can be done? The same program, whatever, suppose have a single task but the single task has to be executed by the multiple processors and all. So that way you need to write a program, or we need to write the application software such that a same program, the single task can be splitted into the multiple entities or multiple smaller programs which are independent, and that can be run on the multiple processors and all. So with that, you can able to reduce the overall computation time. So, and then when you compare here, we are saying that parallel programming, and and we also in this class, in the previous classes, we discussed about the instruction level parallelism and all. So this instruction level parallelism, these things will discuss more detail when you're discussing about a processor and all. So instruction level parallelism is kind of, it's nothing but a pipelining and all. That means you have only one processor, but at a single instance of time, there will be multiple instructions will be executed by a single processor and all. So here the idea here is that we have only one processor, and the instruction for execution of instruction, the instruction has to be passed through the multiple stages of execution, like current kind of fetching, then afterwards reading the operands, then performing the operation, then storing the result and all. So if you can able to compartmentalize these particular different stages, so with that, the multiple instructions can be run parallelly and all. So that is nothing but instruction level parallelism are known to be pipelining, and it is a way of different compared to the ones what we are discussing about parallel programming and all. In case of parallel programming here, they have multiple processes, and each processor has to run the different instructions or like different parts of a same program. So with that, the performance can be further enhanced and all. And here these things are not known to the, like for example, the parallel programming means where the programmer has to write where the programmer who writes the high level language. So he has to explicitly write the program in a way that the program can be consist of different independent the procedures or whatever, so that the same program can be run on a multiple process independently and all. So that is explicitly the user or the programmer has to do that. Whereas the instruction level parallelism and all, that is not to the, it's not known to the programmer and all. The programmer will write a normal instructions, but the sequence of instructions they will be put in parallel, put in sequence to the processor, where there are four. That depends upon the number of stages in a pipeline. So that many instructions can able to run parallelly and all. So that is the way the instruction level parallelism different from the parallel programming in the context of multiple processors and all. So then how to do this the parallel programming? That means here we'll do the programming explicitly for improving the performance. And that is in case of parallel programming, because we have multiple cores are available. So we can make use of the cores effectively. That means even one program can able to run on multiple processes, so that the speed can be improved, or the time computation time can be optimized or reduced. So for that, we need to write a program effectively. We need to write a program explicitly for carrying out that task, like making the program to be like independent parts, and so that each subpart can be run on a different processor and all. So while writing, they have issues kind of a thing, load balancing and all. That means suppose we have a multiple cores are there, we need to see that while splitting the program, all the parts of the program should run more or less of the equal amount of time or equal complexity and all, so that all the process will take almost like reasonably equal amount of time to complete their tasks and all. And at the same time, we should see that the communication between these subparts has to be minimized, or it has to maintain the synchronization. So these are the various issues that arise when you are going for a parallel programming and all. Load balancing and a communication between the parts of the subparts of a program, and their synchronization and all these things are the like overheads that will be taken care by the programmer and all, right? Then these are the concluding remarks. It's nothing but the overall summary of this particular chapter, whatever we had discussed. That means the basic observations, what we learned from this chapter, or what we understood from this chapter, what we conclude from this chapter, kind of a thing. So these things, whatever already we have come across, I need not go through further and all. Okay, so let's switch on to the next thing. Going to the next topic, that is instruction set architecture. Uh, so here basically in this topic we'll try to discuss about the basic instructions that need to be followed by the computer and all, that need to be followed by the hardware just below that. Um, so we have the application software as I mentioned, and then afterwards we have a translator, be a compiler and all, and then the translator will provide you the machine level instructions and all. And these mission level instructions will be understood or can be implemented by the hardware and all. So yeah, here we'll try to discuss about what are these instructions, how they look like, and how the how these how these instructions are represented, how they are coded binary, what are the different types of instructions formats and all those things, and how do we optimize that. So all these things we'll try to discuss very briefly in this under this content and all. Okay, so the set of instructions used by the computer is known to be instruction set. These are kind of language where the computer can able to understand. The way, like for example, we use the words for conveying our messages for our fellow humans and all. Like the way the instructions also happen to be the words where the computer can able to understand. It's nothing but the hardware, the basic hardware will understand those words, and then based on that it will try to perform the task and all. So that way the set of instructions are happens to be kind of vocabulary of a language where the computer can able to understand, right? And then the different computers have the different instruction sets. It's not like too many sets are there and all. That depends upon the way you want to use the hardware and all. So sometimes no, they are like kind of at very gross level. They may be like application specific and all, right? And as I mentioned, like for example, based on the classes of computers and all. So that depending upon the ones where you can also design instruction set to optimize those particular set of applications on that particular computer and all. So that way also can able to use that. And mostly the whatever, even though we have a different instruction sets, but there are lots of common aspects between common aspects among them, because obviously whatever the application it may be, the basic operations will be more or less remain same and all. And so therefore, even though we have a multiple different instruction sets, but there are lots of aspects, lots of issues that are common across the instruction sets and all. And there are like early computers have very simple instruction sets. It's nothing but they will be easy to implement, and the instructions are simpler enough where even though you have a complicated operation, that complicated operation can be resolved into like set of simple operations and all. So that way you can say that the instruction sets are simpler and all. And even the modern computers also follow most of them will follow the similar principle, having the instruction sets, having the simple instructions and all. And here in this chapter, we'll try to focus on mainly the instruction set proposed by the MIPS. And here, this is just the details about that MIPS and all, who invented what and all. And likewise, here there are like at a gross level, there are two levels of instruction sets falls into two categories like RISC and CISC, RISC, and other one is of CISC. It means that RISC means the reduced instruction set computer. It means that the instruction set contains very limited number of simple instructions. It's known to be RISC. And another broad category is known to be CASC, that is a complicated instruction set computer and all, where that particular instruction set contains the various instructions, which includes a complex instructions and all. And again, the difference between them will be like if you have a reduced instruction set, where the clock period can be smaller and all, whereas in case of complex instruction set, where since the instruction involves a complicated instruction which requires a larger time to compute that particular instruction, so based on that you need to set the the clock frequency or like the number of cycles that can be used. So that way you can use it. Yeah, now we'll try to focus on the various instructions that supported by the MIPS architecture and all. And these are like mostly you come across these things at different stages and also, but they are simpler ones. We can go, we can while we are passing through that, you can see that not much difficulty and all, right? So here the first, any computer has to perform the basic operations, not to be arithmetic operations, need to be like add, subtract, and so on. And here in case of a MIPS architecture where this add and subtract will be performed by using three operands and all. Three operands. We'll see that what is meant by operand over here and all. So the three operand, it used to perform whether it's add instruction or subtract instruction, it used to perform on three operands and all. And among these three operands, two are happens to be the sources and one is happened to be the destination and all. So let us see the one of the like instruction which supports the addition operation and all, which performs the addition operation. So add A, comma B, comma C. So here in this add A, comma B, comma C. So here the B and C are happens to be your source operands. That means you need to perform the operation on these two entities or values or variables, right? B and C. And then whatever the addition result you will get, that has to be placed in the destination A and all. A. So that way all these addition and subtract instructions will follow the format like this, where it contains the three operands. Out of these three, two are happens to be your source operands. That means where you need to perform the addition, and the result has to be stored in the other operand and A. And this is the operation to be performed. And all arithmetic instructions mostly follow this particular form and all. So that way it makes that the format will be the like uniform across all the arithmetic instructions. So and another thing is that these operations also very frequent. Most of the times you will come across these arithmetic operations needs to be performed when you're carrying out the program and all. So therefore we here we can use the design principle known to be simplicity favors the regularity. That means we have to follow the regular structure. That means a specific format where all the arithmetic instructions will follow that. And so these are the advantages. Regularity makes the implementation simpler. That means if we have the all instructions follow the same format, then the hardware will become simpler and it can able to access them easily. And the simplicity enables the higher performance at a lower cost. So these are the like the basic principles involved in the designing the hardware and all, because these two are linked, the hardware design and the instruction set. These two are linked. That means the hardware has to perform whatever the instruction set contains. That means instruction set is nothing but set of instructions. Whatever the instruction set contains, all those instructions has to be implemented by the hardware below that. So therefore, when you are designing instruction set, you should keep in mind that what is my underlying hardware and all, or otherwise at the same time when you're designing the hardware also, what type of instructions or what set of instructions I need to be carried out. So that way these two are linked. When you're designing instruction set, you have to see that you should be aware of that what is the underlying hardware, and at the same time when you're designing these two are like mutually depends each other. And let us see the one example so that it will be easier. It will be you can able to follow better. Like for example, in high level language, you have a command something like that where the arithmetic operation that is involved, something like that, f equals to g plus h minus of I plus j, for example. So this is in case of C high level language, you can write this entire thing in one command. But to perform this, to execute this particular command by the machine, by the underlying hardware, it has to perform in multiple steps. It has to perform in multiple steps. So because here this is a combination of this is addition perform over here, again addition, subtraction, and so on. So, but the underlying software can able to perform only one operation at a time. But here there are multiple additions. There are one addition over here, another addition, then subtraction, and so on. So accordingly here, this instruction at a high level language will be translated or will be represented as a multiple simple operations, something like that. So here it may perform first G and H will be addition will be done, and that result will be placed in some temporary place, temporary location T0, right? And likewise I and J will be performed addition, and it will be placed in temporary location T0, T1 for example. And now we have to perform the subtraction of this I plus j from the g plus h. So therefore, we have another instruction subtract where t1 can be subtracted from t0 and the result will be placed in f1. And here, so therefore, these are the two temporary variables, t0, t1, they are the temporary variables where they once this operation is over, then it will not exist. That it will not exist means you can overwrite on that. But here these things f, g, h, i, j, these are the variables. These things maybe can be used later on. We have another instruction maybe like for example, maybe f equals to gh divided by I or something like that. So in that case, again, you need to have the values of g and h. So yeah, we'll see that. So for that purpose, actually, where these values will be reused, how these values can be reused, or where they will be placed, these G, H, I, J, and F values and all. So here, basically, from this, what we need to understand here is that in case of high-level language, a command in high-level language can be implemented by the hardware using in a multiple steps and all, in a multiple simpler steps, right? And now we'll see. Yeah, the next thing is that register operands and all. So here I'm just introducing the terminology register operand. So far, actually, till now, just we have taken a one command, and then we have seen that for execution of that particular command in high-level language by the underlying software, underlying hardware, the basic hardware, will try to implement that or execute that using a multiple sequence of operations and all. Now, how the sequence of operations will be carried out, where those values will be stored. So these things will be resolved by knowing the register set of registers that are there part of the processor and all. So here, as we have seen here, like f, g, h, I, j, these are the variables, right? And now we are performing the arithmetic operation on these variables and all. Like first we will perform the operation, addition operation over here, g and h, then I and j, then subtraction has to be done. And where these variables will be there, right, for performing addition or subtraction by the processor and all. So in the MIPS architecture, where this arithmetic operations will be performed only on the register operands. It means that these values should be there, or these values should present inside the registers. That means as a register contents and all. So for that purpose, the MIPS architecture that supports the hardware that supports the MIPS architecture, it contains the 32 registers, a set of 32 registers, where each register can hold a 32-bit content, 32 bits. So it means that the MIPS, the architecture assumes that the underlying hardware contains the 32 registers, where each register can hold the data of 32 bits, like 0 to 31 number. And these registers are basically used, contains the most frequently accessed data by the processor and all. Most frequently accessed data by the computational unit, whatever. And this 32-bit data is known to be normally called it as a word and all. Like as you know that a byte means 8 bits, like word means 32 bits, and in between the 16 bits is known to be half word and all, right? So this is the nomenclature that will be followed and all. And so as we are seeing, there are 32 registers were there. So among these 32 registers, there are different sets. Again, within that, there are different sets of registers are used for like there is no hard and fast rule, but the compiler or the assembler, it follows the some underlying guideline kind of a thing. Some registers are used for saving the variables and some permanent basis and all, and some registers are used to store the variables on a temporary basis and all. So likewise, there are different registers that are used for different purposes. We'll go through as when you are going through the different the later on, we'll see the usage of the other registers also. So here just we have mentioned some registers. There are like T0 to T9, about 10 registers that used to hold the temporary values and all. that used to hold the temporary values. So here, what is mean by temporary values? Here in this case, for example, you want to perform this execute or implement this expression, for example. Here, this G, H, I, J, and F are known to be variables where it holds some data, right? It has to supposed to keep some data and all. And then, but when you are executing this particular command, you have some intermediate results are there. First of all, you will perform G and H addition, I and J addition, then the subtraction and all. So these intermediate results, whatever is there, that intermediate sums, whatever. So these things will be placed in the temporary registers, T0, T1 and all, right? These are the T0, T1, as I mentioned that these are the variables earlier, but these are nothing but the values here in these variables are stored in a set of registers known to be a temporary registers and all. Temporary, those registers holds the temporary values. And there are some registers that are used for the saved variables. That means those variables will their lifetime will be slightly longer and all. They used to be used, they will be reused later on also. So for that purpose, these registers with named S0, S1, S2 and all will be used. And the way the registers will be like in assembly language or in the language, these assembly language, these registers are represented in the symbolic way like this. Suppose a T0, T1, T2. These are the names, and then the dollar sign before that. So this knows that this indicates that yeah, this is a register, and whenever the dollar sign followed by some two character one, that indicates that it's a register and all. And he see that we use the MIPS supports, we use the 32 registers and all, right? And we mentioned that the registers contains the most frequently accessed items, most frequently accessed data and all. So as we have seen in the case of application programs and all, we have large amounts of data that need to be handled, right? So in that case, but the MIPS or this processor contains only 32 registers and all. So therefore, whatever the most frequently accessed one, that will be placed, and whatever all arithmetic operations has to be performed only on the registered contents and all. Has to be part of a register, has to be placed in the first register, then only it can be accessed. And why there are 32 and all? The reason is that because if we have a larger number of registers to hold, to place it in a processor and all, and again, the problem is that actually if you have a larger set of registers, and again for accessing those registers and all, it will take longer time and all. It will take longer time. So when you take longer time, it means that the clock cycle time has to be increased, So and with that again, the performance will be affected and all. So therefore, one way that actually if we have a more registers and all, then you can keep a lot of data into the registers itself, then accessing will be faster. But at the same time, if you have a larger number of registers, then again accessing the registers, because we have a sequence of registers and all, so we need to access the registers. Again, it takes long time. So where it takes slightly more time. So then in that case, the clock time has to be, or the clock cycle time has to be, more clock cycle time is required to access the registers if the register list is very long and all. So therefore, the smaller is faster. So this is the principle. So for that, based on that, we'll keep the registers will be either 16 or 32. And the main memory will be there anyway, which is away from the processor, which supports the like larger data and all. If you have either instructions or the data, whatever, so you have that will be supported by the main memory and all. So yeah, these are the, so yeah, here in the context of execution of instructions and all, to keep the variables. So all these variables will be placed in the registers and all. Where is that? Yeah, all these variables will be placed in the register as a contents of register, and then these arithmetic operations will be executed on the register operands. Right. Yeah. Next, we move on to, yeah, right. Now you see that the same thing, after knowing about the registers and all, which registers will be used for what purpose and all, then you can, the code, the compiled code or the assembly code corresponds to this particular statement will be this one, because here you can say F, G, H, I, J. So they can be placed in the saved registers. It means that they can be reused later if it is required, right? And the temporary results, whatever G plus H and I plus J, so they will be placed in the temporary registers and all. and then immediately the temporary registers can be used for some other purpose, right? But these saved registers contents will be used, will be used for a later purpose and all. So that way, when you are translating the code and all, the assembly, the compiler and all will try to assign these saved registers to the variables which stay for longer time, and for temporary results or intermediate results will be placed in these temporary registers. Yeah. Then why to perform, or why to keep the contents in the register itself to perform the arithmetic operations? The reason is that because otherwise, suppose we want to perform the addition operation, for example, on the data items that are present on in the memory and all. For example, you have two items A and B, for example, variables. So that was stored in the memory, the main memory, not in the registers, for example. And if you want to perform additional operation, suppose if you design the instruction such a way that, like the instruction like A and B, like add C equals to A plus B, assuming that A and B are there in the main memory and all. So in that case, if you want to execute that instruction, it takes longer time because the A and B, they are available in the memory. And first of all, you need to access the memory, right? The main memory, where main memory is very large memory and all. And you can access the memory and you have to fetch those contents. And then you have to perform additional operation on that. And then the result will be again placed in some other place. Right? Here, the fetching the contents from the memory and all, it takes a larger amount of time. It has to take larger because it has to go out of the processor and again accessing the memory and all, it takes some amount of time and again returning. So that is the reason that all the time these because these arithmetic operations are very frequent. So that is the reason that as far as possible, not the mostly, it's like the way it was designed is that all arithmetic operations are performed on the registered contents, So therefore, since if they are in the register contents, then the entire operation can be performed in one cycle itself. That means, suppose if you perform this, so like add T0, S0, S1, S2, it means that it will perform the the summation of contents of S1 and S2 and placed in the T0. So here the way the operations has to be performed is, first of all, you have to read the contents of S1 and S2. And then on these contents, again, you have to perform addition operation. And the output of addition operation has to be placed in the T0 and all. So all these things can happen within a clock cycle if the contents are, if they are as a part of the registers and all. And suppose if they are like part of, like suppose the contents, the values, if they are present in a memory, and if you want to perform additional operation, it takes longer time because you have to fetch the memory, you have to get the contents, you have to do that. So that is the reason that, and that too, and the add subtract instructions are most frequent occurred instructions and all. Like most of the cases, we have these addition subtraction instructions used to be there. So, and these are frequent instructions. So these frequent instructions has to be optimized, has to be done in a very less amount of time. So that is the reason that these arithmetic instructions are usually operate on the registered contents and all, because the registered contents can be accessed in no time, almost like no time means it in a very less amount of time. That's the reason. Yeah. Yeah. Then memory. Then as I mentioned that again, we have a limited number of registers set. So therefore, we can't manage the entire data with the registers itself. We can't keep the entire program or the data in the registers itself because we have only 32 registers and all. And those 32 registers also meant for different purposes. Some of them holds the data, some of them, as I mentioned, like. So therefore, with the help by having a limited number of registers and all, we can't hold or we can't keep the entire data in the registers and all. So therefore, we use the main memory, right, to keep the composite data. That means the different varieties of data. It may be like arrays, like it may be structures, or it may have some other data, whatever. So all this, the data which is larger in size, which is not accommodated in the registers and all, so that will be placed in the main memory. Right? So since the data is placed in the main memory, so there should have some instructions which used to like transfer the data from memory to the processors and all. Because if you want to perform arithmetic operations and where the data is available in the main memory, for example, so in that case, first of all, you have to bring the data, fetch the data from the memory to the registers, and then and then only the arithmetic operations can be performed, right? Because all arithmetic operations operate only on the registered contents, only on the contents of the registers. So therefore, you should have some kind of a data transfer registers required, and so we'll see those things. So the memory operands means like in the instruction, sometimes we need to transfer the data from a memory to the processor, or sometimes when you perform the processor when you perform certain operation, you will get some result and all. And again, to place the result, the registers are not enough, sufficient enough. So in that case, again, you have to place the result into the memory and all. So therefore, you need to have to perform to execute a program. You need to have instructions where you need to provide some kind of a data transfer between a memory to the processor and processor to the memory and all. So for that to have that kind of instructions, where those instructions contains the memory operands. That means the address of the memory as one of the operands. Earlier, whatever the instructions we have seen, add and subtract, the operands contains the register names because the values are present in the registers. So the register names are happens to be your operands and all, your operands. But here the data is available in the main memory. So therefore, to fetch the data or whatever, to operate on the data, so first of all, you need to index the data. You need to see that where the data is available. So the data is available at certain memory address and all. So therefore, to provide a data transfer from memory to processor or from processor to the memory and all, you should have like the instruction should contain the memory address as the operand and all. So we'll see that what these are. So and again, we for performing data transfer and all, we use the load and store instructions and all. It means that load instruction is meant for loading the values from memory to the registers. That means transferring the data from memory to the registers to the processor will be carried out by the load instruction. The store will be the opposite one. It means the values will be moved from processor to the memory and all, or the register to the memory and all. That will be carried out. That will be done by the store. Load and store. These are the basic operations that will be carried out to transfer the data from memory to the processor and processor to the memory back and all. And the memory, as we have seen, it's a byte addressed. It means that in a memory, as we have seen, we can see, we know the specifications of a memory saying that like it's like 1 GB RAM, 4 GB RAM, like 8 GB RAM and so on. So here B means it's a byte. Like it means that every byte of a memory has a specific address and all. And depending upon the capacity of the memory, you need a certain number of bits to uniquely represent each byte and all, to uniquely address each byte and all, right? So therefore, the memory is a byte oriented, and usually here in the MIPS instructions and all, mostly the arithmetic operations whatever we perform, so those will be performed on the 32-bit register contents, right? So that means most of them, the arithmetic operations what we'll perform is on the 32-bit data. So this 32-bit data is known to be words, So therefore, like sometimes you may fetch the bytes and all, but the majority of the times we will access the data in the form of words, in the form of multiple of 4 bytes and all, like 4 bytes and all. So therefore, can view the memory as sometimes as a word aligned, like in terms of words and all. And then when the memory is aligned in the form of words, then how do you access the memory? How do you represent these words and all? Because if you look at that, as I mentioned, that the memory is basically indexed by the byte addressing. Like every byte has a specific index, a specific address will be there. But as I mentioned that, like most of the times we used to access the data in the form of words. Data in the form of words, which means we will fetch the 32 bits, and again we'll try to store the 32 bits. Most of the times we'll do that way. So in that case, one can able to visualize the memory as a form of a sequence of word level entries and all. Like you have word level entries. That means each entry represents 4 bytes together and all. So in that case, because if you look at in that case, how do you address the memory and all? Like whether you can able to address the memory with the byte at the least significant side or byte at the most significant side. So that way there are like two ways of indexing the memory addressing. The way we represent the memory addressing, one is known to be the big Indian and the other is known to be little Indian and all. So these difference is that we'll see that how it varies and all. You can see the next thing. Yeah, here this is just two. You can see that this is a figure, one figure. This is another figure and all. And here in this figure, you have this is the memory. This is the memory where we have a different and here the words are there. First word, second word, third word, fourth word, and so on. And here the way this is addressed with respect to the words, but this is not correct because the memory is a byte addressed. Like that means every byte has its own address and all, like has a specific address. Like so, therefore, the here this kind of addressing, this is at word level. Like this, you can say that the zeroth word, this is the zeroth word, this is the first word, this is the second word, third word. This is the way you can able. This is the way here it was mentioned as address at a word level, but actually the memory is addressed in the form of byte level addressing. So therefore, this kind of addressing is not correct because we don't use this at all. So we will use the accessing the words in a memory using a byte addresses, using a byte addresses. So that way you can see that here this is the word, I know that, and here this is the again the word means again the 4 bytes will be there. So this is the zeroth byte, and then the first byte, second byte, third byte, and again fourth byte, fifth, sixth, seventh byte. So likewise here, so when you want to access the memory and you want to access the words from the memory, you need to follow the byte addresses and all. You need to follow the byte addresses. So here the previous slide I have mentioned that these byte addresses are ordered in the different ways in the different systems and all. So one way is that actually you are addressing the bytes starting from the most significant side. Here, if you look at here, this is the sequence here. You say that this is the most significant side and this is the least significant side. So if you start the addresses from the most significant side of the word, so then this is known to be the big Indian style. And suppose whereas if you start the addressing from the least significant side, then it is known to be like the little Indian style and all. And here the MIPS will follow the big Indian style. So where it provides the word addresses starting from the least significant byte, starting from the least starting from the byte in the most significant side. That means so this is the byte here. It's the byte 0, byte 1, byte 2, byte 3, something like this, like the byte 0, byte 1, byte. So here this is 0, 4, 8, 12, and so on. So therefore, when you want to access the memory like at a word level, so where the byte, the addresses will be in the form of like multiples of 4, 0, 4, 8, 12, and so on. 0, 8, 4. And you can also access in between also. It's not that way. Suppose you want to access a word starting from the 2, for example, starting from a 2, then it is possible. That means here, in that case, if you want to access a 32 bits, starting from a word to, starting from address 2 means it fetch the bytes from 2, 3, 4, and 5. So that is also that can be done. So usually the memory words are the data will be placed in the form of words. So therefore, where most of the times we'll try to access with 32 bits as entities. So therefore, we'll follow the addresses. That means if the data is placed in the arrays or the structures and all, we'll follow the addresses based on the word level addresses where there are multiples of 4 and all, right? So this is what I mean by the memory addressing, like the byte oriented addressing. That means every byte has a specific address will be there, and then we'll access the memory content either in words or in the bytes also. So, so is it clear? Here the memory is byte addressed, and here the big Indian, little Indian, and also here in case of big Indian, here you can see where is that. Here the addresses will be like this way, like 0, 4, 8, and so on. Whereas in case of little Indian, the addresses will be other way, like here the 3, then 7, then 11, and so on. This is the way the addresses used to be. Yeah. So now by after knowing about the memory operands and all, now let us see an example, a simple C code which involves the arithmetic operation the where the data will be there in the one of the operands of a data that may be there in the memory and all. That is there in the, that is present in the memory and all, right? So here, if you look at here, this particular C statement, G equals to H plus A of 8. So in that G and H are the variables, and A of 8, this is clearly indicates that this is an array variable. It means that usually the arrays will be placed in the, because arrays means it contains multiple data items. So therefore, they will be placed in the memory and all. So therefore, this A of 8 will be is there in the memory, and maybe for a convenience, G and H are available or present in the as the contents of a register and all, right? So, so for doing it, for computing, for evaluating this statement, this addition operation, which involves one of the operand as the memory operand. First of all, and to perform this addition, we know that the addition will be performed only on the registered contents. That means both the values should present as part of a registers, as the contents of registers and all. And again, the destination or the result is also has to be placed in the again the register and all. That is the format of the registered or the arithmetic uh, code, the arithmetic operation that need to be performed with hardware. But here in this case, one of them will be the memory operand. So therefore, the whatever the value that is there in this memory operand, the memory address, that has to be first of all brought into the register, one of the registers. Then we need to perform the addition operation. So for doing that here, the way it will be performed here will be, we know that the A of 8, A is the array name. That means the starting address of the array will be there, will represents the A, right? And then 8 indicates the location of the particular value. That is, it is in the 8th location because it's an array. So it starts from 0, 0, 1, 2, 3. So this is in the 8th location, location 8, right? And now here to fetch the contents from this the array from the array at this specific location 8. So the way it will be carried out will be, because you need to first of all you have to fetch the value from the A of 8 to the register and all. So for that we need to use the data transfer instruction. Data transfer instruction. So we have seen that in the previous slide that the data transfer we use the two instructions. One is load and the other is the store. Load is meant for transferring data from memory to the register or memory to the processor, and whereas the store is the other way, like the data from the register contents to the memory and all. So here we need to first of all have to fetch the data from memory to the register. So we have to use the load. So the format of the data transfer instruction in the assembly will be load word. That means you can later you can see that even you can load the half word, even you can load the byte also. Sometimes that depending on the applications and all, right? So here's a load word. That means you are fetching the 32-bit content from the memory, which is placed in the array at 8th location and all. And array means we know that array has some starting address will be there. And afterwards, we have a word 0, word 1, word 2, word 3, and so on, right? So therefore, so to fetch the like the way the address, the way the instruction of the load will be this way. Load word, that means, and then you need to fetch the word, if you fetch the value from this memory location, and it has to be placed in some register, And this is the temporary register we'll use it T0. And then we have to find out, we have to fetch the value from A of 8. So A has an address, the starting address of the array, and 8 is nothing but the index of the value where it is located. So from the starting, it is at 8th location. And we know that each word occupies like 4 bytes, right? So therefore, to fetch the 8th word means you don't assume that it's a physical 8. It's like actually 9th, but it is as per the index, it will be 8. So therefore, its address will be 32, right? It is at the 32 bytes from the starting address of the A, starting address of the array A and all. Because the first 4 bytes will be the 0th value, then the next 4 bytes will be likewise. If you keep on incrementing, if you look at that, A of 8 will be there, will be available at the address of 32 to 35, 32 by 32nd, 34, 33rd, 34th, 35th. So these 4 bytes constitutes A of 8 and all. And the address of A, that means the starting address of the array, it will be there in the, assuming that it is there in the some register. It is there in the, it is available at the register S3 and all. The starting address of the register, starting address of the array is available in the register S3. It's known to be base address, right? And then after knowing the base address, we have to find out the A of 8, where it is. So A of 8 is nothing but it is at like as a 8th element in array. So therefore, we need to compute what is the actual location in the array. So that is nothing but here as per the index you can able to compute because each word takes 4 bytes. So therefore it is at a 32 byte. So therefore 32. Like whatever the address is there, the base address that is available at S3, and we need to add this offset of 32 to this base address so that we can get the address of the desired word, address of the desired word in the memory and all, right? So therefore here in the load word, the structure, the semantics are something like that. Load word and then the destination register, that is S3, T0 here, because the whatever the value you are fetching that will be placed in T0. And then here it has to provide the two things. One is that S3, it is nothing but which contains the base register, and then the offset. So offset means the value, that means where the value is located in that particular array and all, how far from the base address and all. So that is a 32 and all. So therefore, by using this load word instruction, you can fetch the contents of A8, whatever is there, and placed in the T0 register and all, placed in the T0 register. So now the value of A8 that is available in the register and all, right? And then you can go ahead because the other two arguments are that are already there in the normal variables. They will be available in the registers. So therefore, you can able to perform the add operation. Add, assuming that H is available in S2, right? H is available in S2, and then A of 8 is we already brought into the T0 and perform the addition on these two, and then place the result in S1 and all. So this way you can use the you can when you perform the addition on the like addition where one of the operands is the memory operand, that is the value is present in the main memory. So in that case, first of all, you have to fetch that value into the register, then you have to perform addition operation, right? So, right, okay, then yeah, we move on to the next one, a similar thing. And here where you can see this particular statement, C statement, where it contains the total statement in this particular statement, where here out of the 3 operands, right, the 2 operands are the memory operands, right? That means among these sources, one is from the memory, and again the result has to be placed again into the memory and all, again in the memory and all, right? So for that again the same process and all, same procedure, right? Know that H is a variable, simply variable that is there in the one of the registers, saved registers, and the base address of A is in S3, right? And to perform the addition, we have to fetch the A8 the same way, like load the word and then add you perform, right? And after the addition, then you need to place the result into the A of 12. So A of 12 means again you have to find the offset, that is 48, because 12 into 4, that is a 48 bytes from the starting address, and the base register is S3, and then store, like so you can store the contents of this. So that way you can able to load and store. That means you can use the data transfer instructions for performing the arithmetic operations where the operands are the memory operands and all. Okay, so we'll take a break. Yeah, tell me. Yeah, we'll take a break. Those who want to just take relax, you can go for 5 minutes. You can come back. Yeah, tell me quickly.
Sir, here 48 S3 should be source, no, sir?
48?
48 that in store word, the right side of 48 S3
yes.
is there, no, sir?
48 in brackets S3. The 10 brackets S3 is the base register. That means a register which contains the address
in our
of
code. In our code, A12 is the source, no, sir? We should store the value of.
No, A12 is the destination, right? You see that A12 equals to H plus A of 8. Like here, the arithmetic operation has to be performed on the 2 operands. One is it's available, it's a normal variable, assume that it's there in the register, and other is the memory content. And again, whatever the result you will get, that result will be again has to be placed in the array at the 12th position. That's the
Yes, sir. Then it should come in first, no, sir. 48
where
in brackets S3.
correct 48 brackets 3 should come in the first. No,
Yes, sir.
no, that 48 brackets S3 is that it's nothing but it's a location of A12. It's a location of A12.
Okay.
Right.
Okay,
So
sir.
what we are doing is that in the store word, after we performing this addition, we are with the result of the addition is there in some temporary register T naught. And
Okay,
now
sir.
you are passing the value that is there in the T naught to the location of A12. So that is the one, right?
Okay, sir.
Yeah. Okay, let's take a break and then we'll come back. Right. Yeah.
Sir, I'm like
Uh,
confused with the nomenclature
uh-huh.
using T not T1. Uh, I mean, like the sequence goes like 0, 1, 2,
No, no,
like.
the T naught, no, the T naught T1 and all, you need not follow the T naught T1 sequence and all. But what I'm saying is that when you start the code,
Mhm.
you have a temporary registers that are available from T naught to T9. So you can start using one after another and all, right? That is the way.
And
Likewise,
one more question.
mhm.
After adding, why the temporary sum is stored into same variable, I mean, same temporary register T naught? Why not another register?
No, no, because the purpose of temporary register itself, it's not meant for storing the variable for a longer time, right?
Okay, so
Correct.
after
Yeah,
addition
it's a
of
kind of
register,
it's no, no,
so
it's a
again
kind
we
of
can
again.
use that
Uh,
register.
yeah, it's kind of again optimization. If you use another register, right, then
Mm-hmm.
again we need to go for we have less number of registers, no, because already T naught is there something. So therefore, unless because the T naught it's not used later on. If you want to use it later on, then you can use the like the same thing. If you look at in the previous somewhere in the previous example, if you
Mm-hmm.
see where you are using T naught and T1, both of them, right?
Huh.
T naught and T1. Why we are using here? Because the T naught has to be used later on. So that is the
Okay.
reason that T naught is not used here. So we are using these two temporaries over here, and then we are adding these two temporaries and we are placed over here, and that is the way.
Okay, sir.
Right? Okay. Yeah. Let's take a break and then we'll meet. Yeah, after 5 minutes. Okay. Yeah. Yeah. Okay. Okay. Hello. Welcome back. So shall we start now? Hello. Yeah. Hello. Hello.
Yes,
Yes, sir.
Yeah. So shall I start now? Yeah. Yes. Okay. Yeah. Yeah. Let me. Okay. Yeah. Now, yeah. This one we are discussing like memory operands, where an instruction contains two memory operands, and one requires the load and other requires the store word. Yeah. Then basically whatever we come across we discuss, because we have used the register operands, and we also use the memory operands. So this is just to see the like rationale behind using these two operands and all. Yeah, as you know that, yeah, the same thing whatever we come across, registers are faster to access than memory. So therefore, the most frequently accessed contents will try to place it in the registers. Uh, and operating on memory data requires loads and stores, and where it requires more time, right? And the compiler must use more instructions are required. As you see that, suppose arithmetic operation that involves memory operand and all, you see that it requires it is again split into the two instructions, or sometimes three instructions. That depends on how many memory operands were there and all, right? And yeah, that's the way. Like for example, if the instruction contains a three memory operand, then we have some more additional instructions are required. And the compiler must use the registers for variables as much as possible. That's true, uh, because the accessing registers will be faster, as we already know that, and that too, the number of instructions also will be reduced if you use the registers and all, because as we have seen that if all contents are available in the registers as a simple variables, then the entire arithmetic operation can be carried out in one instruction itself. Whereas if it involves a memory operands, then it requires additional instructions and all. Right. So therefore, as far as possible, we use the register contents, and only the spill to memory of the less frequently used. Yeah, this is obvious thing. Like if the data is large, and in that the most frequent data will try to place it in registers, and the other data which is less frequently used variables and all, that will be placed in the memory. And the register optimization is important. That's true. Yeah, because from this, what we understand is that one way we had to increase the number of registers to hold many data items so that the accessing will be faster. But at the same time, if the number of registers are increases, again, as I mentioned that you need to have more access time to have registers. And because the registers are very frequently accessed, so therefore we had to optimize the time to access the register. So therefore that aspect will try to make sure that the registers has to be limited, less number of registers and all. So based on that, the registers will be considered as 32, not more. Uh, yeah, then go to the next one. Yeah, right. Yeah, right. So then, yeah, the next one is that so far we discussed about the instructions that involves the operands are either present in the registers or present in the memory and all. And there are certain instructions are in the normal high level language. Most of the there are many places, or most frequently we try to perform these addition or other arithmetic or any other operations using some constant. Using some constant, we do that. For example, in the loops and all, we'll try to increment the variable for every loop to check that how many times the loop has been done, right? So likewise, there are many instances in the normal programming where we involve the constants, where we make use of constants very frequently and all. So in that case, we have specific instructions in the MIPS because these instructions are frequent. That means more frequently they occur, like where the operations need to be performed on the constant, So in that case, we design again some other instruction type or instruction where it supports the constants. That means whereas so far we discussed the operations are supporting only the content as a part of contents of registers or as content of a memory content, as a content of memory locations. And this is a new one, the other one, other variety, where the operations are performed on the operands where one of the operand is constant. That means directly we are using constant as one of the operand and all, right? And so otherwise, one way is that actually we can keep this operand again in the register, and again you need to use that. Again, for moving this content constant into the register, that again takes one more additional instruction and all, right? So instead, actually here you can use the constants directly as a part of the instruction where the entire instruction will be executed in one cycle or in a unit amount of time, right? So that was the, and because why we are using this as a special instruction, different instruction, because the reason is that because the involvement of constants in the instructions are more frequent. So therefore, we can compromise the design or we can able to make a provision for the another type of instruction where which involves one of the operand is a constant and all. Because this is different from the regularity, because as you see that earlier in the regularity where we have the three operands will be there, or arithmetic instructions are performed on the three operands and all, right? Whereas here, if you look at here, this is like one of the operand is constant and all. So this way, like so this instruction, suppose we want to perform here, the operation is that. So one of the that means here, for example, suppose I equals to I plus 1, for example, I equals to I plus 4, for example, where I is a variable and you want to add 4 to that, right? And so the variable will be placed in one of the register. 4 is a constant, and then you can able to perform the sum and placed into this one, right? And here, suppose if that this provision is not there, where the operand can be a constant, in that case, what we have to do, we have to place this operand first into a register, some other register S2. So by using some other instruction, and after that, then S2 and S3 will be added, and then you have to place it in S3 and all. So, and then this operation has to be performed very frequently. Suppose in case of loop, for example, where every iteration you have to perform this one. And in every iteration, whenever you used to perform this one, you need an additional instruction is required and all. So to avoid that, actually, you can have the another instruction format where it allows one of the operand happens to be constant. Operand happens to be constant. So here this is known to be add immediate in this case, because one way that this name add immediate symbolically, it's that we are immediately adding the constant, right? We are immediately adding the constant like the value and all. Whereas earlier and all, the value has to be placed in the registers. Suppose if it is the memory, then it has to be brought into the register. You have to do that. But here you can able to perform the addition immediately with the register content as one of the like operand will be a constant and all. So this is add I, right? And so this can be done. And similarly, a subtract immediate also can be carried out, but there is no separate instruction for subtract immediate, because here the constant you can able to represent either a positive or negative constant and all. So therefore, based on this mechanism, the same add I can takes care of both the immediate and subtract both add immediate and even subtract immediate also can be carried out using the add immediate only, because here the constants will be either positive or negative. We can able to represent the constant either positive or negative using the representation, 2's complement representation. So that way, suppose if it's a positive constant, then it will be incrementing. If it is a negative constant, it will be like kind of a decrementing kind of a thing. So we can able to do it with the same instruction itself. We can able to do that. So and yeah, here is that the principle that is involved to go into the another format will be like because of make the common case faster and all, because here this is the these type of instructions or these type of tasks will be more frequent. So therefore, to make it these things to be faster, you can have a small compromise or a small change in the deviation from the regularity can be allowed and all. Like a small constants are common all the time, and not only that, this particular format we can also use it for load and store instructions also. This immediate operand, whatever is there. So here if you see that in this immediate operand, how many registers are there? There are two registers, right? And then one operand is there, one constant operand is there, right? So here the similar thing you can also use it for like load instruction also. We'll see that when you are discussing about the instruction format, you will come to know that this particular the immediate operand, whatever the instruction format that is required for this immediate operand, the same format can also be used for load and store. Why? In case of load and store, if you remember that there is offset will be generated, right? There will be offset that will be added to the base register so that you will get the actual address and all. So that offset can be represented as a constant here and all similar to that. So that way, even the load and store instructions also have the similar format of these immediate operands and all, like the instructions which handles the immediate operands. A similar format will be there, but they will be distinguished based on the function, that's symbolic. Like here add I means it indicates that the functionality to be performed will be like adding over the other contents, like over the operands and all. Whereas the load is nothing but that indicates that based on that particular code, a particular instruction symbol, we can come to know that the operation to be performed will be like transferring the data from that particular address to a desired register and all. So that way you can distinguish, even though they have the same format. And all. We'll see that those things very clearly later on. And there is one more important thing in the MIPS. Among these 32 registers, there is a register 0, 0th register. So it is hardwired, and always it contains the value 0 and all. It always contains the value 0. That means even though you transfer the value, even though you add, like for example, you use a 0 register, and yeah, for example, you use 0 register and you add something to 0 and again place it in the 0 register, still it will not allow. That means here, what I'm saying is that the specific register 0th register, where it always holds the value 0 and all. It means this value will be used to just to like take the value of 0 from the register. In that case, you can use the 0th register and all. And this register has different applications. You can use this 0th register as one of the application, like moving the contents and all, right? No, what I'm saying is that here in the MIPS, where one of the registers will be known to be 0 register, where the content of the register will be always 0. You can't write anything. You cannot overwritten on that. It's hardwired such that all the contents of this register will be always 0 and all, right? So what is the use of that? There are different uses. Sometimes, no, for example, you want to compare something. You want to compare some result with a 0 and all. At that time, you can use this 0th register where, because it always holds the 0 value. You can always content the 0th register with some other, whatever the expected the result outcome and all. Suppose you want to take some decision where the result will be there. If the result is 0, then you need to execute some part of the code. If the result is non-zero, then you execute some other part of the code. At that time, for comparing with the 0 and all, you can use the 0th register as the content and all, as a part of the operand and all, right? And another use is that common use is that moving between the registers and all. That means suppose you have some value is there in some register, and you want to transfer or you want to move that value into some other register, for example. Like for example, here in this case where you want to transfer the contents of S1, register S1 into the other register T2, for example, other register T2. The way you can able to perform here is that there is no separate move command or move instruction is not there in the MIPS and all. It will be internally will be taken place by using the arithmetic instruction itself, add instruction. Add S1, 0 register and then the result will be transferred to or will be moved to the register T2 and all, because this is the destination register. These are the two source operands and all. So one of the source operand is S1, whatever the contents of S1. The other operand is 0, that is 0th register and all. And so you can use the sum over these two, and whatever the result is there, that result will be placed into the T2 and all, right? So that way you can, this is nothing but just moving the contents from one register to the other register and all, right? So so that way you can use the 0th register for moving purpose from to the into the registers, and comparison purpose sometimes you can use the 0th register. So likewise, so for this, since it is a multi purpose and more frequently that is used, so therefore one of the register is hardwired such that always it contains the 0 and all. You can't overwrite it. So this is a part of optimization when you are designing the instruction set and all, like so in that case, based on the nature of the operations and all, so most of the times you require the 0 value. So instead of again taking the 0 value somewhere from the input or whatever, so instead you can use it directly over here. Yeah.
So the
tell me.
So the load and store instruction is also doing the same thing, right?
Yeah, that we will discuss later and all. We'll see that. How the load and store instruction have the similar format of the ones immediate instruction. We'll see that. I'll just show you. Like, just wait for a few slides. Yeah, yes. Then these slides actually I'm not going to discuss much actually here. These are the ones what you have covered in your digital electronics and some other subjects also most of the times. And this is very primitive one, so I don't want to spend much time. Just I go through. For example, if you have unsigned binary integers where the values, if you want to represent the integers, for example, using unsigned, and if you have 32 bits, so the maximum and minimum, the limits are 0 to 2 power n minus 1. It's a very straightforward. N is the number of bits, and here in this case is the 2 power 32. So therefore, this is the range of integers if you denote the values in unsigned format and all. In unsigned format, if you want to represent the data, then the maximum, the range of data, the values that can be represented will be this one, straightforward. That is unsigned. And in case of signed one, it means that you have a data where you have both in the signed notation. That means it represents this particular representation or notation involves both the signed numbers as well as unsigned numbers and all, right? So in that there are different ways you can have the signed representation can be done using 1's complement, 2's complement and all. And now the most of the computers are all the computers by default, they are using the 2's complement notation for representing the signed integers and all. So in these signed integers in the 2's complement notation, the way it will be represented will be, suppose for example, you have 32-bit number, right, in the 2's complement. So its value will be represented as whatever the most significant bit is there, that will be taken as a negative, that is minus of x of n minus 1. This is nothing but the bit value into 2 power n minus 1 plus, and whatever the remaining bits are there, so that will be like added up. Like so this gives you the total, the actual value of the binary number in the 2's complement. So because that, how you got that one, if you look at here the 2's complement number, where is that? Yeah, where you can able to see that the 2's complement number, where you can able to see with this notation you can get its actual value and all, its actual value. And with this, sorry, this is unsigned one. Sorry, yeah, this is the signed one. In this signed one, where the most significant bit that offers the negative value, that means the total that gives you the negative value, the maximum negative value, and then whatever they're following that, what are the bits that are following that other than the most significant bit, that gives you the magnitude corresponds to this one, the positive one, and then the subtraction of these two from the most negative to this one, that gives you either a positive value or a negative value and all. So here in this case, if you look at here, if the most significant bit equals to 0, if the most significant bit equals to 0, then in that case what happens? The value will be positive. All the time the value will be positive because the most significant bit is 0. So therefore 0 multiplied by 2 power n-1, the negative is nothing but 0 only. And whatever the leftover, the bits under that contributes to the magnitude or the value in the positive direction. And if it is a 1, if the most significant bit equals to 1, then the values that are resultant from that from the 32-bit number will be a negative one, because this gives you the maximum negative value minus of 2 power n minus 1, right? And this is the maximum negative value, and the combination of remaining all bits will be less than this one all the time. So therefore, when you add this maximum negative value to the remaining contribution by the bits and all, always it will be negative. So that way, if the most significant bit equals to 1, in case of 2's complement, it indicates a negative number. And if the most significant bit equals to 0, it indicates a positive number and all. So that way, accordingly, you have a ranges and all. You can see that in using a 2's complement, the range of numbers that can be represented will be, because it represents both negative and positive. So that's the reason that you can have the range will be minus whatever you can see to this one. And if you look at here, the negative range is slightly one more than the positive range. Positive, because the 0 is added here and all. So therefore, so the positive range will be the maximum number, the positive number that can be represented will be 1 less than the most negative and all. The most negative. So this is the 2's complement notation. I'm not going to the details of that. So please go through that. There are like the several books used to give the details, you know, please go to that. I'm not going to discuss about this. Then the sign negation in the case of 2's complement, how the negative number can be. Suppose given a 2's complement number, how do you get a negative number of that? You can able to do this by using this logic control. Simply that the way is that the given number in the binary notation, if it's a 2's complement number or given number, if you want to find out a negative number in the corresponding negative for a 2's complement, you simply flip all the bits of the number and add 1 to that. That gives you the 2's complement opposite sign, negative, right? If it is a 2, you will get a minus 2. If the given quantity is minus 2, then you will get a plus 2 and so on. And then sign extension. Yeah, this is important here. Here sign extension means when you're dealing with the numbers in arithmetic operations or other cases and all the time, the numbers will not occupy all the 32 bits and all. Sometimes the numbers may have only 9 bits. Suppose you are taking a constant, for example. The constant may have 9 bits in the binary representation. But when you perform addition of a constant to some other registered content, the other register content contains the 32 bits, but here if a constant represents 9 bits, you cannot perform addition, because as per the addition, you know that the addition will be performed on the 2 operands which have the same bits, same number of bits. So in that case, even though sometimes the constant has some number which contains a lesser number of bits compared to 32, we have to make it to be 32-bit word. We have to fill that the other bits also. So in that case, we use the sign extension and all. So it means that what we have to do is that representation number using more bits. That means, as I told you, for example, we have to add 4, like I plus 4, for example. 4 is a constant here and all. So when you try to add 4 to this I, where I value is there in the register, that's a 32-bit number. And your ALU, arithmetic logic unit, will try to add only 2 32-bit numbers. When you're giving a 32-bit number from the register, which indicates the value of I, and you want to increment that I plus 1 or I plus 4, for example, where you use the immediate format instruction where the constant 4 will be there. But when you add 4, the 4 can be represented by using only 2 bits, 3 bits, right? With the 3 bits, you can able to represent 4. But you cannot represent that constant with a lesser number of bits and cannot perform addition directly. So to perform addition, both operands should have the same number of bits. So in that case, how to generate the 32-bit number from the value which offers only the lesser number of bits and all. So in that case, we use the sign extension. What it means here is that whatever the sign bit is there, you just replicate the sign bit for the remaining number of bits. For example, you have a 4, you have minus 4, for example, or 4, for example, 4. And you want to add this 4 to some other register content. The 4 is nothing but 100, for example. In a signed bit, in the case of 2's complement, it is nothing but 0100, right? And if you want to add this one to the register content, it should have 32-bit number. So this 0100 has to make it into 32-bit is nothing but the 0 is nothing but sign bit. That sign bit has to be replicated to the remaining bit positions, because since you need the 32 bits and you have only 4 bits are available, so remaining 28 bits will be filled up with will replicate the sign bit and all. So that way you can use the sign extension to make the value to the desired number of bits and all, right? And yeah, the same thing. This is useful. The sign extension is useful in all these instructions. I have mentioned like add I, like add immediate, where the constant can have a smaller value, which can be represented by using a fewer bits. But to perform any operation and all on the other registered contents, this operand also has to be 32 bits. So therefore, you need to have sign extension is required, right? You need to extend the immediate value. Likewise, here also. Like for example, in case of load and store also, you can see that in case of load and store also, where if you want to perform load and store, where you need the offset has to be added to the register contents and all, and where the offset is a constant value, right? Either 32 or whatever. And you want to perform the addition of these things and all internally, it has to again sign extension has to be carried out. Likewise, the BUQ and BNE, these are the other instructions that, which are based on the conditional statements. We'll see that later and all, don't worry about now. So BUQ is another branch on equal and branch on not equal. So these two instructions also requires the sign extension and all, right? Whatever the result you will get, so that result has to be compared. So in that case also you need to have the extension of sign is required. So basically here sign extension means you have a number where you can able to originally represent with a fewer bits, right? And to use that number for some other instruction, so in an instruction where you want to perform some logical operation or some branch operation, some other thing, where that number has to be there in the form of 32 bits. So the transforming the lower number of bits, which represents a value, to a 32 bits again represents the same value. So for that purpose, we use the concept of known to be sign extension and all. So with that, the value will not change at all. Here you can see that the actual 2 will be plus 2 is nothing but actually 0, 1, 0. So the sign extension is nothing but this one. And assuming that originally it is 8 bits are available here. 8 bits of 2 is available here. And here this 08 is the sign bit. And now you want to extend it to 16 bits means the sign bit will be extended. That means sign bit will be replicated in the other bit positions and all. The same way, if it is a -2, for example, in case of 2's complement representation, -2 is represented by these 8 bits, like 7 bits, 7 ones, like followed by like 0. Right? This is the -2. And if you want to represent this -2 from 8 bits to 16 bits, it's nothing but the sign bit, whatever is there, that has to be extended. Right? So this way you can use the sign extension to represent the value in the multiple formats, in the multiple bytes, like either 16 bits of word or a word, whatever. Right? Okay, yeah, now we come to the point. How do we, so far we discussed about basically 2 formats. One is the normal arithmetic instructions, which contains which handles the 3 operands, and all the operands are in the form of registers and all. And there is other instructions known to be immediate instructions, where one of the operand is constant and all. One of the operand is constant and other operand may be registered, right? And likewise, in case of load and store also, we have a different format. We'll see that how these instructions are actually represented. And we represented so far in a symbolical way, right? In the symbolical fashion, because when you say add, you say that add like S0, S1, S2, something like that. So this is a symbolic representation. And this representation is again not followed, not understood by the actual hardware, because the actual hardware understands only zeros and ones. Only the sequence of zeros and ones will be understood by the actual hardware. That gives you that like a presence of pulse and absence of pulses are given a signal or absence of a signal. So that way the hardware works on the digital signals and all. But for our understanding point of view, the instruction, because if you have a sequence of zeros and ones, 32 bits, So it is difficult to see that what is happening and all. So therefore, for our understanding, so slightly better understanding, for our convenience, we represent these binary 32-bit binary words in the form of symbolic instructions, symbolic way. Those are known to be assembly instructions. So that whatever we discussed so far, like the add, like so and so registers, or like load register comma sum offset and followed by this one. Likewise, immediate add I something. All these are the instructions in the assembly language, are known to be symbolic instructions and all. And these instructions are supposed to be converted into binary, and those actual the sequence of binary numbers, these binary bits. So that those are the actual instructions to the hardware, right? So now we'll see that how do we encode that and all. So yeah, these instructions are encoded in binary called a machine code. A machine code means it's like ones and zeros. The instruction in the form of strictly ones and zeros is known to be machine code, and the instructions in the symbolic form is known to be the assembly code. Right? So the MIPS instructions encode. There is a all MIPS instructions are encoded into 32-bit instruction words. Whatever may be the instruction, whether it may be like arithmetic instruction, or whether it may be a load store instruction, or it may be like immediate instruction, whatever, or it may be some other conditional one. Later on we can go through that. So all the instructions has to be represented by using 32-bit instruction words, right? And so that means whatever the instruction will be, the instruction will be represented by using a sequence of 32 bits. Because there are several reasons for that. Because they are 32 bits, because they can easily fit into a register or easily fit into a word in the memory and all, right? So that is one thing. And not only that, if all instructions are 32 bits, then the accessing the different fields of instructions or accessing by hardware will be simpler and all, because all will follow the same thing. So we have a similar circuitry, or one circuitry is required to handle all these 32 bits and all. And then in these 32 bits, like there are smaller number of formats for encoding the these 32 bits represent the different fields and all, like the 32 bits all together, where they represent individually. If you go inside among these 32 bits, the first 6 bits may represent something, and the next say 5 bits may represent something. So likewise, we'll split this 32 bits, or we represent 32 bits in the form of different fields and all. Like for example, as we have seen, add S1, S2, S3, for example. So where add specifies the operation to be performed, and this S1, S2, S3 indicates the register values and the contents of registers and all, are nothing but the identity of a register and all. So when you try to encode that into 32 bits, somehow we have to represent that, since we know that there are only 32 registers. So to represent or to identify each register, we need to have 5 bits are required, right? So in the case of add S1, S2, S3, we need to have 3 register operands are required, where each register operand can be encoded by using 5 bits, because there are 32 registers altogether, right? By giving 5 bits to each of the registers, you can uniquely represent all the registers and all. So the binary representation is nothing but just encoding that symbolic representation of the instruction in the form of ones and zeros and all. So we'll see that how you do that. And the 32-bit words and the smaller, as I mentioned that these 32 bits represents the different fields, like 4 or 5 fields and all, where each out of that, as I mentioned, that add represents one field, like R, S1, S2, S3, each of them represents separate fields and all. So that way you can able to represent these 32 bits. Yeah. Then the register numbers, as we have seen earlier, we have seen there are 32 registers are there, as I mentioned. But for a symbolical representation, as for our convenience, we made the made the register number register names as something like T0 to T10, T0 to T10 as a temporary ones, S0 to S7 as a save registers, and there are other registers used for some other, like 0 is one of the register, for example. Likewise, there are other registers are there, and since there are 32 registers, all these registers are encoded by using the unique number from 0 to 31, right? Anyway, the 0 register is indicated by 0, and here the T0 to T7, they are represented by like 8 to 15, the value, the number 8 to 15, And T8 and T9 are represented by 24 and 25, and S0 to S7 are represented by 16 to 23. So likewise, all these registers, 32 registers, are encoded uniquely with the 0 to 31, right? So always S0 to S7 means they are S0 is represented by 16, S1 is 17, S2. So likewise, these 8 values corresponds to S0 to S7. Likewise, the T0 to T7, T8 to T9, and there are other registers. We'll see that later. And now by knowing this, now we'll come to the representation of instruction and all, like how the actual 32 bits are arrived from the symbolic representation and all. So the 32 bits in case of these are known to be R format instruction, because here the operands happens to be all 3 registers and all, right? The operands are happen to be all the 3 registers and all. So this is known to be R format instructions and all. And all arithmetic operations are performed on these R operands and all. With all 3 operands happen to be your R. The contents of registers and all. So for this R format instructions, the format will be like this. There are total 32 bits are there, and out of that we know that there are 3 registers involved in that, right? RS, RT, and RD. Where here RS and RT happens to be your source operands. RD is your destination operand. So, and the first 6 bits indicates the operation at a very gross level. So what it means is that, for example, your arithmetic operation add and subtract. So they will both come under the arithmetic group. So for all of them, this opcode will be remain same. And the function field here over here, this will be like will distinguish among the arithmetic operation, whether it's add or whether it's a subtract, something like that. So likewise, this operation and function field, these two will together will distinguish the different operations and all. These first 6 bits, the most significant 6 bits indicate the opcode. This most significant bit indicate the opcode. This provides the at a broader level what is the operation that is involved, whether is it the arithmetic instructions, or whether it's a logical instructions, or whether is it the load store instructions involved with the memory, or is it the kind of control flow like if then else kind of checking the conditional ones, right? Branch instruction. So all these things will be resolved by using these 6 bits and all. This is a broader category and all. And sometimes within this broader category, there will be subcategories can be resolved by using this function field. So therefore, this is the opcode, and this is known to be function field, which involves 6 bits and 6 bits. So there the total 12 bits will be there. And then these R format instruction contains the 3 register operands. That means there are 3 specific registers will be there, right? And each register can be encoded by using 5 bits because there are total number of registers are 32. So therefore 5 bits is enough for encoding the register identity. So therefore 555 and so on. And then there is another field, another remaining 5 bits are there. These remaining 5 bits are used for indicating the shift amount. Anyway, for these arithmetic instructions, we don't use this field and all. So therefore, for all arithmetic instructions, wherever this shift field is not applicable, so in that case, all these 5 bits will be filled up with zeros. All these 5 bits will be simply zeros. And wherever the shift related instructions will come there, it will be non-zero and all. So that indicates that how much shift you have to be to it. Suppose you have 32-bit number is there, right? And that 32-bit number, the 32-bit value, those bits, if you want to shift right or left, for example, then that will be indicated by using this shift amount and all. Using this shift amount, you can able to use that. You can able to represent that whether to shift left or shift right and all, right? And so this is the way the all R format instructions used to be there, as I already mentioned over here, right? And now you can see that how do we encode these simple one of the assembly instruction and all, like for example add T0 S1 comma S2, right? And as I mentioned, this add here this is nothing but this is the format, and in that we'll try to like encode the corresponding values. Here these are the 2 source operands S1 and S2. So you have to give S1 and S2 values, whatever the codes are there, whatever the register numbers are there, so those has to be placed over here. Similarly T0 here, and since it is arithmetic instruction, so the shift operand will be 0. And this is the specific this is the addition operation. So the function code corresponds to add will be here, and this is the op code corresponds to a broader arithmetic instruction. So therefore it will be here. In this case it is 0 and all. Right. So here now you can try to encode these things, each of them. So the 0, the 6 zeros, then 17, 18, 8, all these are encoded with 5 bits and all. Then so now these 32-bit sequence. So this is the actual machine code corresponds to this addition operation and all. Addition operation. And in these 32 bits, we have seen that this is the first 6 bits that indicates the what is the type of operation. From this itself, we'll come to know that what is the format, mostly what is the form by knowing these 6 bits itself, whether the format will be R format, or whether the format will be some other immediate format, or format will be some other there is other branching instructions will be there, other format. So all these things will become to know by using this opcode itself. Then accordingly, by knowing this opcode, we know that what is the format. Then the corresponding controller or whatever, the hardware and all, it will fetch the corresponding bits, and then it will use it for their consumption. It will fetch the first 5 bits used to indicate read the value from this register, and next 5 bits used to read from the register, and these 2 values are used for addition. The ALU will perform addition. Then the sum will be again placed in this register T0, where that is indicated by these values. So that way the internal hardware will take care of the individual fields of the bits in this 32 bits and all. So this is 32-bit sequence binary, and this is the corresponding hexadecimal fashion, because representing 32 bits instead it will be easier, where the 4 bits together can be represented by using one hexadecimal bit and all. So that way this is hexadecimal notation. Hexadecimal means base 16, right? So 4 bits of binary can be represented by using one hexadecimal bit. So that is the way you can do that. This is just for simplification, simple notation, right? The same thing here. This is just how the hexadecimal notation will be there. And I'm not going to discuss. This is trivial, right? Then coming to the I-type I format instructions. So far we discussed about R format, where it contains the 32 bits, how they split into the different fields. And now coming to the I format instructions, you can able to see. So in case of I format, the first 6 bits remain same. Opcode represents the operation. And then following that, in case of I format, you have the 2 registers will be there. You have the 2 registers. The first register will be the source register, because in case of I format, we have seen that to perform addition in I format, one operand will be available from the register. Other operand is a constant. Other operand will be a constant, right? So therefore, you need to have some source register is required, and then the result of that addition with the constant, that will be again placed in some other register, right? So therefore, you need to have one more register is required. So in case of I format, you need to have 2 registers are required, and anyway opcode and a constant. And here in this case, the constant for a constant representation, we have given the format as per this format allows 16 bits and all. Allows 16 bits for representing the constant and all. 16 bits for representing the constant. And this constant will be, as I mentioned, that this can be either positive or negative, right? In the 2's complement form, it is represented. So therefore, it represents a maximum negative number as -2 power 15, and the maximum positive number is 2 power 15 minus 1, right? So that way this one. And now these are the 16 bits. So this way, the immediate format instructions are represented, right? And now, as I mentioned, that the same immediate format is also I format is also used for representing the load and store instructions. Load and store instructions. How they are represented? In case of load and store, as you remember, the load instruction, for example, you have to fetch the content from a memory and you have to place it in some register, target register, right? Some register, right? And also from which address you have to pick up. So for that, you have some base address will be there that is available in some register. and then there will be some offset is there. That means from the base address, which location or which value has to be picked up. If suppose if the items are in the array and all likewise, right? So that way here in case of load and store instruction also, the same format can be applicable. That means this opcode, which specifies that whether it's a load or store or immediate or add immediate or subtract immediate, all these things can be discriminated by using this opcode, right? And after that, in case of immediate, we need to have two registers are required. Either it may be immediate, either it may be like add immediate or whatever. Or even for the load and store also, we need the two registers are required. One is that to store the to keep the contents in the from memory contents into a register, and second one is that the base register. That means the address of the address of the base address which contains in some other register. It's known to be base register and all, right? And then anyway, offset will be there. That offset will be will occupy these 16 bits and all. That offset will be occupied this 16 bits and all. So that way, even the load and store instructions also can be represented by using this I format. And you can see that this follows the like a design principle. Good design demands the good compromises and all. So because you see that now you deviated from the R format, right? But again, we have followed the regularity as a 32 bits. Even the R format or I format or even some other format also, all instructions should follow the 32 bits, should have 32 bits. But here we have slightly deviated from the R format because of the good performance. Because otherwise, actually, if you want to use it in the same format and all, it takes longer time, much longer time. So here, for that purpose, here we deviated from that. But we followed to some extent, we followed the regularity because there also, if you look at the R format also, after the opcode, the two fields will be represent the registers. There are three fields representing registers there, but here we we require only two registers. So therefore, immediately after the opcode, then we have the two fields, 5-bit fields, which indicates the register contents and all. It is almost similar to the R format. That means the first 16 bits of R format and the first 16 bits of I format represents the same. Represents same means represents the similar fields, almost same fields. And here the last three fields of R formats are clubbed together, and that will be given for representing a constant or the address, offset address. So therefore, this is what given here. Different formats complicate decoding, but allow 32-bit instructions uniformly. That's what. And keep the formats as simple as possible, right? So because we are deviating from the other format because the reason is that we want to perform, because the many times we need to perform addition with a constant or subtraction with a constant or something do with the constants. So therefore we have to compromise going to some other format other than the R format. So that way we take in this one, right? Okay, so. And finally, this is the simple one, the generic one. As you know that in a computer, like all of them are stored in the memory and all. All of them are stored in the memory, whether it may be like whether it may be high-level language, right? The normal high-level language is also stored in a computer, stored in a memory somewhere, right? And afterwards, to transform this high-level language, whatever the compiler is required, that compiler machine code is also present in the memory, right? And afterwards, whatever the compiled code of these high-level language, even that is also present in the machine in the memory. So, and even the data instructions, all of them are stored in the memory itself, and then the processor will make use of to execute the relevant commands at relevant time. Suppose for performing compilation, then the compiler code will be executed by the processor and all. Then you can get the output will be machine code will be there. And once you generate the machine code, then the machine code will be processed by the processor and all. And when the machine code is processed at that time, the required the data items and whatever it is, it will be fetched from again from the memory and all. So what I mean to say is that everything will be there in the memory itself, and the processor will be processed, will process these different entities at a different times, different points of time and all. Right? So this concept is known to be stored programmed concept and all the computers will follow this very generic thing. So yeah, we'll stop here, right? It's now around 11:55. So we'll stop here and we'll continue this in the next class. And whatever the slides I'm using, as you know, that all these slides are taken from the textbook itself. And maybe I have missed some of the points and not covered the things. So please go through that. And as I mentioned, the two's complement and all those things, I have not given enough time. And since it is all of you are come across that at a different points of a time, if you're not done, then please go through that and refresh it again. So we'll stop here at this point of a time. Yeah. So now you can leave, go to the next class, you can leave some, maybe, if at all. And if there are any queries, those who don't have any other class and all, we can have it for another 2-3 minutes. Yeah, let me, yeah, let me stop the recording. Yeah.